let's look at this Alka-Seltzer tablet. Your goal is to make that dissolve. What would you do to help change its solubility? Okay, maybe you would raise the temperature. If you raise the temperature, then your solubility is still going to be the same, because the solubility is the number of grams that will dissolve, right? So at that temperature, that is the solubility. So you're not really changing it by changing the temperature. You want to keep the temperature the same and dissolve more of this. What would you do? Well, there are a few things you can do. One of them is called the common ion effect. Okay. In this case, the Alka-Seltzer tablet has some bicarbonate, or it's a base, HCO3- in it. So if you already have HCO3- in the water before you add the tablet in, you will actually dissolve less of this because there's already the same ion in the water. So because of the common ion effect, you would then decrease the solubility. So solubility. Let me rewrite that. Solubility. Okay, that's an I. Okay. Another way you can change this is by changing the pH. Okay. Since HCO3- in the tablet, this is HCO3- is a base, if you put some acid in here, it'll react with that and it'll make it dissolve more. So by changing the pH, you could increase or decrease the solubility depending on what you have. Okay? The next one is by binding that ion to make something called a complex ion. And I will show you examples of that later. Okay, so let's talk about each of these three. The first one is the common ion effect. What will happen to the solubility if that ion is already in the beaker before you add the solid? So here we have let's say you made some calcium fluoride in here. So let's say you have F-, F- in there, and you're putting a chunk of calcium fluoride solid, CaF2 solid. What's going to happen is the solubility will go down because there's already ions in there, and it's going to push this equilibrium. So CaF2 wants to dissolve into Ca+2 and 2F-1. If you already have some of this, it'll push this equilibrium to go left, which means you will dissolve more. It'll stay together as a solid. Okay? You can also have other ions in there. Let's say you have calcium hydroxide, Ca+2, OH-, and you're trying to drop some calcium fluoride in there. Same thing, CaF2. Because Ca+2 is also a common ion, it'll also make it dissolve less. Okay, so it doesn't matter if it's the positive ion or the negative ion, either one will lower the solubility. Okay, if one of the ions in a solution equilibrium is already dissolved in there, in the solution, the equilibrium will shift to the left. So go this way, and the solubility of the salt will decrease. Okay, so let's go ahead and do a problem. Calculate the molar solubility. So here they want moles per liter. You know what I remember? I remember I did this problem incorrectly here. I gave you the molar solubility here, but they didn't want molar solubility. They wanted grams per liter, which is no problem. I can take the molar solubility, which is, let me just do it here, 2.1 E negative 4. The molar means moles per liter. If I want to change that to grams per liter, all I have to do is change the moles to grams of CaF2, and that will get me to grams per liter. So just get the molar mass and you multiply and you'll get the answer. Okay? For this problem though, they do want the molar solubility, so that's what we'll find. So you want to dissolve CaF2 in a solution of CaNO3. So if you were to analyze the beaker, what is the common ion? Yeah, CaNO3, calcium nitrate, has calcium plus 2 ions, and so does CaF2. The nitrate is not common, so I'm not even going to write it. So that will affect the solubility. So let's write the equation. CaF2, you want to see the extent of that dissolving. Ca plus 2 plus 2F minus 1. So you're going to do an icebox. So initially, what do you have in the beaker already? Well, it says there's 0.01 molar of calcium plus 2, right? So I'm going to put that here. There's already that in there. But there's none of this. Okay? So you're going to do, how much of this will go to the right, will dissolve? So you're going to do plus x, plus x. So it's 0.010 plus x, and then x. So KSP is equal to Ca plus 2, F minus 1 squared. Oh, you don't write this down because it's a solid. Just ignore that. So let's plug it in. KSP is, I think it was given from the other problem, right? Yes, right here. 3.9 E negative 11. So we'll just write that here. This is going to be 0.01. Okay, so this is really small, negative 11, so this is going to be negligible. I'm not even going to write it. And this is x squared. Okay, all you have to do is solve for x. 3.1 E negative 5. Now, what's important is you know what that is. This is x, which means you just found, oh no, I messed up. This should be a plus 2x. So this should be 2x. This should be 2x. And the square should be on the outside. Oh no. Okay. That's how you should do it. Okay. So now when you solve for x, you will get this number because I just got that from my paper. Okay. So this is, x is the molarity of F minus 1. So this is the molar solubility of, oh no. Oh, this is x. So I have to solve for 2x because F minus is 2x. So the molar solubility for, if you double this, will be 6.2 E negative 5. This is the molar solubility of F minus 1. Okay? So if you want the molar solubility of CaF2, you just have to do a ratio. For every 2 moles of F minus 1, you're going to get 1 mole of CaF2. 1 mole or 1 molar, same thing. Okay, moles per liter, it'll be the same thing. Let me just use molar so it cancels. So this is going to be molar, molar. This cancels. Divide that by 2, you're going to get 3.1 e negative 5. This is the molar solubility of CaF2. Okay? With the common ion present, with that ion present. Let's go ahead and look at the molar solubility if there's no common ion. That's the previous problem. So in this problem, the molar solubility with no common ion is 2.1 e negative 4. So 2.1 e negative 4 molar CaF2 with no common ion. This is the molar solubility with a common ion. So what happened to the solubility? Yes, the solubility went down with a common ion. So it didn't go to the right as much. Some of it went to the left. So you don't get as much of the ions. You don't get as much as of this dissolving because there's already some ions in there. Okay? Pause the video and try this yourself. Calculate the molar solubility of CaF2 in a solution that has some NaF in it. So write the equation, CaF2, Ca plus 2 plus 2F minus 1. This is NaF, so you have some F minus in there, which is 0.01. And you don't have any of these. Okay, so CaF2 solid will go to the right, so it'll be plus X. And don't forget, plus 2X, that's what messed me up last time. So this will be X, 0.01 plus 2X. And so 3.9, KSP is equal to 3.9 e negative 11 is equal to Ca plus 2, which is X, and this squared, right? So I'm going to call this negligible because KSP is very small, so it'll be 0.01 squared because of this 2 right there. So X is equal to 3.9 e negative 7, and that is the molarity. This is X, this is the molarity of molar solubility of Ca plus 2. Okay, the question is asking the molar solubility of CaF2, so I'm going to go ahead and do a ratio. For every 1 molar Ca plus 2, you get 1 molar of CaF2. So you're going to have the same number, 3.9 e negative 7 molar CaF2 dissolving. So that's the amount of this dissolving. This is called the molar solubility of CaF2. How many moles for every 1 liter will dissolve of CaF2?